write this as minus del prime dotted into P over R plus del prime dotted into P over R. And again, R here is identical equal to the magnitude of R minus R. So this is what I have. So this derivative, if you see, when I take del prime of this quantity, which is of course an R prime, right? And this is an R prime. Then I'm going to get a gradient, not a gradient, the dot product of del prime with P over R, and then I'm going to get what I want, right? Plus P times the gradient with respect to prime of 1 over R, which is this term. So the fact is I have to subtract this term in order to get that. So if we write it in that form, then I get that V as a function of R, then I can write it as 1 over 4 pi epsilon 0, and now I get two terms. One term is the integral over the volume of minus del prime dotted V over R prime plus the integral now of this other term, which is del prime dotted into P over R, right? dv prime. And so I use now the divergence theorem, and what I do is I'm going to rewrite this term that I have, which is now the divergence of P over R. I'm going to rewrite this as the integral over the surface enclosing the volume V of P dotted into the normal of that times dA over R. So that's from the divergence theorem. So then I end up with a volume term, and I end up with a surface term. And I have not defined how did I get P or anything like that. All I'm saying is that I can have a polarization vector which is dipole over the volume, which could be, an inhomogeneous anisotropic function. And this is what I get exactly. I didn't make any approximations of this. I just used the formula for what the potential to the dipole moment is. So now, what is this? So now that we have these two terms, define, and this is very important, a bound, we're going to call it bound, charge density, which comes basically from the polarization. Okay? And so this is evaluated on R prime, and this is R prime. And a surface, bound surface charge density, right? Which is then equal to P dotted into M. If I define these two things, and this now you have to remember this. Why do we call it bound? Because these are not moving charges. These are charges effective, in some sense, surface charge density and volume charge density that is due to the polarization itself. The polarization is the thing, it's the physical thing, right? This is basically the divergence of that I'm going to call bound, and the normal component of P on a surface I'm going to call sigma bound. And it cannot move. This is not a plus and a minus charge, and what you expect is that the integral of rho bound should be 0. Right? That should be 0 because you don't have any bound charge. Plus or minus is basically what you ought to have. So what we get then is a phi then, P of R, I then can write as 1 over 4 pi epsilon 0, the integral of rho bound of R prime over R minus 0 prime, dv prime, plus the integral over the surface enclosing this thing of sigma bound, right, dA prime over R minus. This is what we get. So let's do, I'm not going to get to one example which I want to get to. Okay, imagine that you have an interface, and here I have P1, and here I have P2. And so I have some interface in here, so the outward normal, I'm going to define it from 1 to 2, okay? So in this case, I'm going to have a sigma bound, which is, in this case, is going to be equal to the normal, or dotted into P2 minus P1, all right? And so you can imagine, since from my definition here, that I can write this as n is dotted into that is equal to sigma bound 2 minus minus sigma bound 1. Okay? With respect to that one. So I have some vector, and I have some vector. So P2 is in this direction, P1 is in that direction, so P1 and P2, the outward normal is what I get this term. Okay, so now let's go on to a little bit more definition. So this is something that is very important, right? So this, all the problems then get reduced to this with these conditions. So we have gone on chapter 5 a bunch of problems where we have solved Laplace's equation, right? In the case in which what was on the right-hand side, there was no surface charge density or volume charge density in the region where you were calculating this, right? So now we go back to what we did before in chapter 3, where now you have to evaluate potentials due to charge distributions, okay? And so we're going to do a case of a sphere that has a permanent polarization that is constant, okay? But before we do that, what happens then to Poisson's equation in this case? So what we have was before is del dot E, remember, has to be equal to what? In this, on the right-hand side. It should be rho total now over epsilon 0, which is equal then to rho free plus rho bound over epsilon 0. Okay? This is what we have. So if this is the case, I can write that this is equal to 1 over epsilon 0 times rho free minus del dot P, the polarization vector. So let's put then, multiply this by epsilon 0, and then get the following. So I get that del log epsilon 0, which is a constant times E, plus P should be equal to rho free. This is exact. So define a displacement vector which is equal to epsilon 0 E plus P. So then my equation then goes down to del dot D is equal to rho free. This is what I got, right? So I cannot make any sense out of this problem unless P is proportional to E. So for the cases that we have seen in which the polarization is always proportional to the applied electric field, then I get a circular sort of thing in which I say, wait a second, I can write that P then, right, is equal to, in this case, we're going to write it is proportional to E, but this proportionality constant, I'm going to write it like this, where this guy is called electric susceptibility. And it's the most important quantity that I can have, right? So if this is the case, what you're saying is that the polarization is proportional to the electric field, and end of the story. In general, as I keep applying the electric field and increase the amplitude of the electric field in a system, what happens is the polarization vector no longer is proportional to the electric field linearly, but it could depend on E squared, E cubed, and high order terms, and this is what we get into the nonlinear regime, okay? Also, it doesn't have to be isotropic. So in general, this is what we're going to assume. It's isotropic. So in general, what you have is that the component alpha of this thing, you can write it basically as epsilon 0, the sum over beta, so chi alpha beta. It's a tensor. That is in general. In other words, in what we call piezoelectric crystals, as you know, you basically can apply an electric field in some direction, right? And the polarization vector has components not just in that direction, but in the transverse directions. Also, when you squeeze it in some direction, you can produce an electric field in another direction, right? So it's not necessarily homogeneous. So when we have a homogeneous system, then we have a linear, isotropic, homogeneous dielectric, right? What we mean by this is it's linear, meaning that it is proportional to E, no E squared or E cubed or no. It's isotropic, meaning that basically now in any direction is proportional to E. So if I apply it in the X, I get this. If I apply it in the Y, I get that, and so on, right? And homogeneous is because chi here does not depend on position. It's the same everywhere, okay? So for those cases and those cases only, you can imagine I have three conditions: linear, isotropic, and homogeneous. For those three cases, then we have then that D here then should be equal to epsilon 0 of E plus chi P, right? Sorry. Right, there's 1 plus chi E. And so I can write this basically as epsilon 0 kappa E, where kappa here in this case is the relative permittivity. And this is then epsilon E. And epsilon then is, we call it absolute or whatever, but it's electric permittivity. Okay? So this is D. So we will use this to find in problems the relationship between the conductor and a dielectric, okay? And so we're going to do now, I think, 7 problems or 6 examples, which is we're going to go through these in the next lecture. And I didn't want to go through that with a PowerPoint presentation because, as you know, there's a lot of material here. So if I show you one slide or something, we miss a lot that can't really be conveyed in one slide. And so in the next lecture, then, where we're going to do our examples of this, and so you have to recall 2 things. One is that this is the expression that we have no approximations. I don't know what P here is. It could be no linear function of polarization vector. It could be a permanent dipole moment. It doesn't have to be induced, okay? So if it's a permanent dipole moment, when we look at magnetic field, you can see that the magnetization in a hard ferroelectric is it's a value like a magnet, a permanent magnet, right? So think of a magnet when you're thinking of P here, and so the magnetization in a permanent magnet is constant. If you apply temperature, or it might reduce it. If you apply a magnetic field, you might change it and so on. But it doesn't go to 0 just because the applied magnetic field goes to 0. So you have something, and when you calculate the magnetic field out of this quantity, you don't need to apply anything to it, right? So here is similar. If I had a P that is permanent, right? Even if rho free was 0, I would generate an electric field because I have a potential that is generated out of that permanent magnetization or polarization that I have, right? And if I have B, the electric field E, right, is still minus del V. It has to be. So that's what it will be. Okay? And so now imagine that if I do this here, from this thing, I'm going to get precisely what? That if this guy is equal to 0, what happens? Say E, there's an E here. So what happens if you have a P that is not equal to 0? Where is this E coming from? So we will go through examples in which we analyze what is an apply E, what is not an apply E, an E that it is basically created by this polarization vector going okay? Which you can see is implied in this, right? Because E, remember, was rho total. And rho total has a rho free and a rho bound, right? So then what happens if rho free is 0? Rho bound is minus delta of E. So then what is E equal to? It should be given by P, right? If you look at this equation, of course this is a differential equation, but you can see that this gas modulo epsilon 0 is P, right? So we'll go through some of these examples because I think that without the examples that we do, I think it's very meaningless, so it's 7 or so. We will not, some of these things are not obvious because of the boundary conditions. So some of the boundary conditions are a little subtle. Questions? Okay. So this is a big approximation. Linear isotropic homogeneous.